discussing a paper about 3D reconstruction from 2D images by a postdoc here at Stanford. The details are in the show notes. The idea is that you take a picture from a car, a tree, a mouse, and you reconstruct a 3D version of that picture. You generate a three-dimensional version of that picture, just taking an image. Later in the paper, they discuss even the idea of text to 3D. So give me the picture of a mouse jumping from a tree, 3D reconstruction. Three-dimensional means you have depth information, you have shadow information, you have things along those lines. So interestingly enough, also the author calibrates this by camera. So this is even by different camera versions generalizable, which means that you can take any picture taken from any camera and reconstruct a 3D version. The interesting thing about this paper is that one is the methodology, and then the applications in VR, AR, and gaming, and also robotics, because we here at Orange Capital Partners, we're mainly interested in robotics, and VR and AR are actually the kind of cousins of robotics, because with 3D reconstruction, by having three-dimensional representation, a robot can learn how to grasp something. A robot has depth information. A robot has spatial information in 3D, which is exactly what reality looks like. So we can then use that for the simulator to train the robot to grasp or to walk or do those types of things. The same thing with a car. Driving through space in 3 dimensions, whether it's in virtual or in the real world, becomes much closer to each other because of the ability of better 3D reconstruction. To take a picture of a tree and then reconstruct a 3D version. What that means in practice is that you have to find a way to generate a 3D version of a 2D image. Now, the actual technique that is used in this paper is twofold. One is it's using a so-called LRM, which is a large reconstruction model. And the idea of LRM, it's a sort of a parallel to LLM, and it uses a transformer-based architecture with cross-attention, self-attention, and other layers that take a tokenized input. In the case of images, they use patches. This is based on a paper that originates at actually Facebook at FAIR, where they use patches of images as tokens and then run it through a transformer architecture to generate, to reconstruct images. Now, the 3D part comes in a so-called triplanar reconstruction. So you take the 2D image and you reconstruct the pixels in a triplanar, so in a three-dimensional space. The additional innovation in this particular paper that I'm discussing is a diffusion-based generation. So you start with tokenization, you run a transformer architecture through it, and then you use diffusion to reconstruct the image. Now, the purpose of this episode here is really twofold. Let me say what is not the purpose, right? I am not necessarily trying to explain the engineering challenges of this particular work, and I'm also not testing whether it's really working, whether it's good or not good, whether it should be a special paper at CVPR or anything like that. This is not my task. I'm not a researcher, I'm not an academic. I am interested in making money with robotics. So this is the fundamental idea. So why are we doing this? Why are we discussing papers, presentation, and so on and so forth? The idea is that We want to understand where is the science, where is the engineering, and what is possible. The fundamental idea at Orange Capital Partners, the purpose of Orange Capital Partners is to invest in fundamentally new concepts and engineering practices with a hope, with a goal of generating wealth. Now, we have two main pillars on which we're basing our investment. They all are combined under one rubric, which is autonomy. And then they split into energy transformation and liberating humans from menial work. So those are two different goals that we hope to achieve with the same fundamental rubric, which is autonomy. Autonomy means AI. It means a little bit more than AI. AI has many different applications these days. AI is imagery, construction, gaming, virtual reality, chatbots, but it's also robotics, and it's robotics where we're interested in. This is our interest. Robotics in the self-driving car space and robotics in the humanoid robot space. We believe that imagery construction, which is the idea of this paper, is important because it will help us create simulators. And we believe simulators are important because that will radically increase the speed of training. So I hope this is very, very important. So I want to bring this point across. We are interested in image reconstruction, 3D rendering of images, generation of images. All these kinds of tasks have the ultimate goal of helping us build better simulators, more realistic simulators, but also more efficient simulators, right? Because if we want to have a simulator that can simulate trajectories for robots, we have to have the ability to reconstruct a huge number of trajectories in a computationally efficient manner. So this is the sort of the backdrop. Now let me get back to this paper. Again, this is based on a presentation by a postdoc at Stanford. Details are in the show notes. The idea is that you take 2D images and you use a transformer-based methodology and diffusion to reconstruct 3D images. There is an implicit assumption here that there is structure to be gained by pre-training a transformer-based model from 2D to 3D. There's some structure, some latent representation or transformation from 2D to 3D that then can be used for zero-shot learning and to generalize for all kinds of images across all kinds of cameras. Again, this is the idea. This is the hope. And the experiments show that that's possible. So the same way that you have training of large language models that then help you generalize across all kinds of tasks. In other words, you can have a chatbot. You can have very specific question-answer sessions. You can have very specific tasks to be executed based on the learning of a pre-trained large language model. And because that's possible with language, people thought about doing the same thing with images. And it looks like that, at least in the first instances, that is actually a possibility. So you have a certain latent structure in a 2 to 3D transformation that can be applied in a general way to many, many more potential pictures and images and representations. Now, the question, of course, then becomes, okay, you want to have an ability to generate a 3D representation of a 2D image. How can you do that computationally efficiently? So one is it doable? And transformer architectures have shown to be successful at that because they actually are able to capture this latent relationship between tokens that help generalize from 2D to 3D. But then how can we do this in a computationally efficient way? In particular, at inference time. We don't want to have to go through every patch and recalculate every possible combination of patches and do these massive dot product calculations. Is there more efficient, are there more efficient applications? And this is where the diffusion kicks in. And this goes back to my conversation I had with Jeff Dean from Google at the MLSys conference when he spoke about diffusion as a possibility to have more energy efficient inference. The new architectures could be applied with diffusion just in order to save at inference time. Inference time is a big one. Inference time is, the idea is that you can have very large models representing a lot of knowledge, but can you efficiently search through this knowledge base at inference time to find the most relevant information that you need to generate whatever you need? Let's say in the case of reconstructing a 3D image from a tree, you don't want to go through all possible representations of tokens that have been trained in the model with all kinds of different types of images. So diffusion, now what is diffusion? Diffusion is the idea of denoising an image. So you start with random noise, and then you have learned, think of it like, I like to think of any kind of image problem in the sort of, in the filter way. You've learned a filter to look at a noisy picture and filter out what represents a cat. And the way you do this is through denoising. So the denoising parameters are really the filter. So, and now you of course, you can go deeper. You can learn what it means to denoise a cat, the cat sitting in a restaurant, the cat sitting on a bike. You have all these possibilities with Gen AI to be creative. But fundamentally, the idea is that you learn a filter, and the filter allows you to apply Gen AI to your task. Now that's computationally more efficient because the filter, by definition, by the essence of the word, is filtering out already what is necessary for the inference, so you can potentially save on computation. Now, I'm definitely on thin ice here, and I think not just me, I think the whole science community is still in a try and error space when it comes to using diffusion as a potential generative tool to save on computation costs. It's not clear what can be gained, but what is being lost. I mean, we can gain a computation time. We can, always basically reduce wall clock time, memory requirements, energy efficiency. All of these things can be gained, but then we don't know exactly what we're losing. But I think this is worth just noting as a conversational topic for future ideas and thoughts, and also with preparation to CVPR. It's definitely one thing that I'm going to be paying attention to, which is the computational efficiency of inference and potential shortcuts to that. I'm going to finish this episode just by summarizing the importance of image generation for simulators, which is really the holy grail. The simulators are the goal. The goal is to have an ability to represent reality, so robots can learn in virtual space how to behave. Robots can also learn physics from virtual space. And the reason we want to do this is because it's just a lot more cost efficient and much more powerful. We could then have very general algorithms that can train robots to do all kinds of things and potentially come up with many Move 37 type actions, because we have the ability in virtual space to train embodied agents with a much more in much more efficient ways. Thank you.